Welcome to the next lecture on machine learning for core engineering disciplines. In the last few lectures, we have introduced ourselves to the concepts of artificial intelligence and machine learning, and we also discussed how probability and statistics play such a major role in AI and ML, right, whether it is for conventional applications or for core engineering disciplines, and that is because a lot of the processes that occur around us are stochastic. So, in the last class we introduced the concept of a random variable, and then we looked at a number of associated things that can be defined, like the probability density function and the cumulative distribution function, right. So, in today's class what we will do is we will introduce some examples of random variables, whether they are discrete random variables or continuous random variables. Now, what is the link to ML? The link to ML is that in machine learning we are trying to develop a function approximator, right, that will predict the output of a certain process based on a set of features, right. Now, typically we do not know what is the underlying distribution of the target variable, right, but in some cases it helps to get an idea of roughly what distribution it follows, right. Now, there are several standard distributions that exist for discrete variables and for continuous random variables. So, we will start our lecture by looking into those, right. So, let us begin our journey. So, we will start looking at some example probability distributions. And like I had already mentioned, in machine learning you can either work with a regression problem, which is to predict a continuous variable, or you can work with a classification problem, which is to work with a discrete variable, discrete target that you want to predict, right. So, analogously in probability and statistics there are discrete random variables and there are continuous random variables. Right, and typically you would be dealing with a discrete random variable when you are working with a classification problem, and you will be dealing with a continuous random variable when you are working with a regression problem. So, now let us look at some example distributions that can be discussed, right, and we will begin with the discrete probability distributions. So, let us look at some of the discrete probability distributions. One of the simplest example that can be considered is the Bernoulli distribution. So, in the Bernoulli distribution, it is the simplest discrete distribution modeling a random experiment with only two possible outcomes, right. So, it is a random variable with only two possible outcomes, right, and let us say these are success, which you denote with a 1, or failure, which you denote with a 0, right. So, for example, this Bernoulli distribution could represent the probability of getting a head when you toss a coin, right. So, if you have a random variable x, right, to denote that it follows the Bernoulli distribution we will use this tilde symbol, and then we can write it as follows BERNP, and this P is a parameter of the Bernoulli distribution, and this P lies between 0 and 1, right. So, this P actually represents the probability of success. This is the probability of success, right. So, if we were to write the outcomes that can happen. So, the probability of the random variable capital X taking a value small x is p if small x equal to 1, right. We just discussed that this parameter p represents the probability of success, and obviously then the probability of failure is 1 minus p if x is equal to 0, right, and these are the only two possible outcomes. So, the probability of x being any other variable is 0, right. So, p of capital X equal to small x is 0 if small x is neither 1 nor it is equal to 0, right. So, obviously this is the simplest possible random variable, right, discrete random variable that you can think of, and we motivated this example using that of a coin that is tossed and you are looking at what is the probability of success. Say you define success as getting a head, then small p is the probability of getting a head. Now, if it is a fair coin, then we know that small p is equal to half, because there is 50% chance of getting a head, 50% tail. However, if it is a biased coin, right, if it is a loaded coin, meaning one side is heavier than the other, then this small p need not be 0.5, need not be 50%, and you can have less or more than 50% chance of success and vice versa for the failure, right. So, this is the simplest probability distribution that one can discuss. Having discussed this, let us go on to the other possible discrete distributions. The second one that I would like to introduce is the binomial distribution. Okay. Now, in a binomial distribution, what it really does is it generalizes the Bernoulli distribution to n independent and identical trials. Right, and I am sure you may have encountered this kind of a distribution in the past, right. Let us say someone tosses a coin 10 times or 15 times, and then you are trying to find the probability of a coin appearing a coin taking heads a certain number of times, then that is the binomial distribution, right. So, you are generalizing the Bernoulli distribution to n independent and identical trials, right, and again each of these trials has a probability of success equal to p. So, each of the trials has p as the probability of success. Right. So, then x, right. So, if you denote that the random variable capital X follows the binomial distribution, right, that is characterized by the number of independent and identical trials n and the parameter p, which is the probability of success in every trial, right. So, this x then represents the number of successes in n independent Bernoulli trials. Okay, and obviously each with a success probability p. Okay. So, then the probability p of the random variable x taking a value equal to k is equal to nck p to the k and 1 minus p to the power n minus k, right, and k here can be either 0, 1, 2 up to n, right. And you may have seen this distribution here, and why this probability looks like this is because you have to account for k of the n trials succeeding, right, and each of them are independent trials and identical. So, you can multiply p k times. So, that is the reason for p to the k, p to the power k, and also n minus k of the trials should fail, right. The probability of failure you know is 1 minus p, and then you need to fail n minus k times. So, that is 1 minus p to the power n minus k. So, you would think that that is the entire piece, but then there is this very important part which also tells you that the order, right, in which the trials are occurring is not important, right. So, any k of the n trials can lead to success. So, that is why you have nck appearing here, right, and obviously you all know, right, what the expression for n choose k or nck is, right. You all know that nck, which is also denoted like this, a large parenthesis enclosing n and k, this is equal to n factorial divided by k factorial times n minus k factorial, right. So, this is the binomial distribution which is also encountered quite frequently, right. If you can imagine that there is a Bernoulli trial, right, an event which has only 2 possible outcomes and we are repeatedly doing that, then what is the random variable that comes out of it, that is the binomial distribution. Okay. I hope this is clear, right. Now, let us go ahead and learn a few more discrete random variables, right. So, the third discrete random variable that I would like to discuss is called the Poisson distribution. And this distribution is very important, especially for engineering disciplines, because it represents the number of events that occur in a fixed interval of time or space, right, assuming that there are events that occur independently and at a constant average rate, right. So, oftentimes you know the rate of a certain process and you want to predict how many times that process happens, right. This process could be a reaction, could be like the failure of a certain component in an electrical circuit or the failure of a beam, right. It is a random variable and you want to know how many times it occurs, especially that you know the average rate at which the event occurs, right. So, it is a very important distribution in engineering disciplines. So, the Poisson distribution models the number of events occurring in a fixed interval of time or space, assuming each event occurs independently and at a constant average rate. Okay. So, we denote this as the random variable x following the Poisson distribution characterized by a parameter lambda, and then this lambda is basically the rate parameter. It represents the average rate of the process or event, that we are trying to model. And I gave you a number of practical examples. It could be the failure of an electrical circuit, failure of a beam, or it could be a reaction that happens every few seconds, something like that, right. So, the probability mass function in this case, so the probability of your random variable capital X taking the value k, this is given as lambda to the power k e to the minus lambda divided by k factorial, right, and k is basically the number of times the event occurs, right, and this can obviously be 0, 1, 2 and so on, right. So, this is a very interesting distribution and has a number of practical applications, right. And the last distribution that we will sort of discuss is the geometric distribution. Again we are discussing these distributions that are followed by discrete random variables. We will come to the case of continuous random variables a little while later, right. So, this distribution models the number of Bernoulli trials needed to get the first success. Okay, so that is the geometric distribution and it is denoted as follows: a random variable x follows the geometric distribution with the parameter p, right. We already saw this parameter p in the Bernoulli distribution. We know that this represents the probability of success and it is between 0 and 1, right. And in this case for the geometric distribution, the probability of x taking the value k is equal to 1 minus p to the power k minus 1 times p, where k is 1, 2, 3 and so on, right. And like I said, this distribution is encountered when you want to get the number of trials, right, in a binary event that is needed to achieve the first success, right. So, hopefully this gives you an idea of the kind of discrete random variables that you will have to work with, and I already alluded to this. The function that is akin to the probability density function, that is called the probability mass function here, right, probability mass function, right. And you already seen such kind of examples earlier, right. When you roll a die, you can get any outcome between 1 and 6, that is a random variable, and then in that case the mass function is equal to 1/6 1 divided by 6 for numbers 1, 2, 3, 4, 5 and 6, and for any other number the probability mass function is 0, right. So, this is just to sort of get you warmed up to the concept of probability and statistics, which is so central to the field of machine learning and how to apply it in statistical scenarios. Okay. So, with that thought, right, let us move on to continuous random variables, because like we discussed, in many of the cases we do want to predict the outcomes of continuous variables in regression problems. So, that should be the next place where we look at, right. So, let us come to continuous random variables. Okay. Again, there are a number of continuous random variables that one can encounter, and obviously you may have encountered some of these before. So, this is primarily to act as a refresher for you in case you have forgotten these concepts. So, the first continuous random variable we will discuss, or the continuous distribution that we will discuss, is the uniform distribution. okay, and this uniform distribution, right, it models a continuous random variable which is denoted as x following the uniform distribution with two parameters a and b, which has equal probability to lie anywhere in the domain A to B, right. And usually when you generate a random number on the computer, I am sure many of you may have generated random numbers in MATLAB or in Python. Usually the function that is available is a uniform random number generator. It generates a random number between 0 and 1, and of course anything you get between 0 and 1 can be scaled to lie between A and B, right. So this forms the basis of all random number generators, right. So in this case we will talk about the probability density function, right, unlike the discrete random variables where we talked about the probability mass function, right. So the probability density function this equals 1 over b minus a if x is between a and b, and it is 0 if x is less than a and 0 if x is greater than b, right. So this is the probability density function, right, quite straightforward, right. That is how it has equal probability, it has equal probability anywhere in the domain from A to B, and it has 0 probability to lie anywhere outside the domain, right. And one can write down the corresponding cumulative distribution function that also we had discussed in the previous lecture. So if you want to write capital X, which is the cumulative distribution function, and if you remember, this represents the probability that the random variable has a value that is less than small x, right. So the probability that the random variable has a value that is less than a is equal to 0, and then if you are between a and b, then the probability, right, the cumulative probability goes as x minus a divided by b minus a, and finally, right, when you pick any number that is greater than b, the probability, the cumulative probability up to that point becomes 1, right. So this is the cumulative distribution function, right. So the uniform distribution, like I said, carries a lot of weight. It is the simplest possible random number generator function that you will encounter in any programming language, given it whether it is C, C++, Python and so on. And if you have to sample a random variable, right, that is from any other distribution, you can use a formula or a method to convert one probability distribution to another, and that is also something we will briefly touch upon. Now moving on to other distribution functions that are sometimes encountered, the most common one is the normal or the Gaussian distribution. Okay. So it is one of the most commonly encountered distributions, right. It is also known as a bell curve, right, and essentially, right, it follows this kind of a pattern, right. So x is following a normal distribution that is characterized by a mean mu and a variance sigma square. So this quantity is called the mean and this quantity is called the variance, right, and this is commonly known as a bell curve, right, which represents one of the most commonly encountered distributions. And there is a reason for why this normal distribution function is so commonly encountered, and that reason is called the central limit theorem. And this theorem, simply stated, tells that the normalized sum of many independent and identical distributions tends to the normal distribution. Okay. So, due to this central limit theorem, right, you take any sort of random variable, right, and then you combine lots of those random variables together, and finally for many such independent and identical distributions you will get the normal distribution or the bell curve, right, and it is known as the bell curve because it really looks like a bell, right. So, if you plot this probability density function, right, as a function of x, it will peak at x equals mu, right, and it looks something like this. Okay. So, if you write down the probability density function for x which follows a normal distribution, then it is 1 over root 2 pi sigma exponent of minus x minus mu whole squared divided by 2 sigma squared, right. And like I said, mu is called the mean of the distribution, and sigma is called the standard deviation of the distribution. I already told you that sigma square is called the variance, right. So, the square root of the variance is the standard deviation, right. And like I said, this is so commonly encountered that yeah, you would have noticed it many times, right. Some examples are, for example, student marks in an exam. If you have a lot of students, typically their marks will follow the normal distribution, right. There will be very few students with a very high grade and then very few students with a very low grade, and the majority of the students will lie in this middle region, right. So, that is why it is a normal distribution, right, normally represents a lot of phenomena going around us, and then there are so many other examples, right, height of people in an institution. Or if you want to come a little bit closer to the molecular level, then the distribution of atomic velocities in a fluid, right, that also follows something that resembles a normal distribution, right. So, now there are a few more distributions, right, that are followed by continuous random variables, So, we hope to look at them. The next one I want to discuss is called the student's t distribution. Right. So, this distribution is particularly important, right, because it is very useful in determining the confidence intervals for a linear regression fit. To find the range in which the true mean of a parameter lies, right. So, what it does is it basically quantifies the extent of deviation from the true mean, right. So, this distribution quantifies the extent of deviation from the true mean. Okay. So, therefore, it is defined as t equals x bar minus mu by s divided by square root of n, where I will define these quantities shortly. So, this random variable t is following the student's t distribution, right. So, this is the random variable following the student's t distribution. X bar is something known as the sample mean, right, which is defined as 1 over n sum going from I to n of x I, right, the average of the n outcomes, right, of the random variable, and s squared is something known as the sample variance. It is defined as 1 over n minus 1 times the sum of all the deviations from the sample mean, right. So, this is the student's t distribution, right, and it is quantified by one parameter, that is n, right. So, the student's t distribution is quantified by the parameter n, or equivalently the parameter mu, which represents the number of degrees of freedom which equals n minus 1, right, because 1 degree of freedom is lost in defining the sample mean, right. So, this nu is the number of degrees of freedom. So, your probability density function f of t is given as gamma function nu plus 1 by 2 divided by nu pi times gamma of nu by 2 times 1 plus t squared by nu times to the power minus nu plus 1 by 2, right. And for those of you who do not know what the gamma function is, do not worry, the gamma function is defined as follows, right. Obviously, if this looks a bit complicated, it is okay, right, you may be encountering it for the first time, but that is okay. As you go on in the course, you will see that you will be able to handle more and more complex things, right, and this is used to define, right, x minus 1 factorial, and in this case x need not be an integer, right. So, that is how the probability density function of the student's t T distribution is defined. Okay. Now there are a few other distributions that can be discussed. However, this is an introductory course and therefore I do not want to delve into them, but I will just state their examples before we end today's lecture, so that you know that these do exist. There is something known as the Poisson distribution, right, and it represents the probability of an event. So sorry, the Poisson distribution was what we discussed earlier. Its counterpart, the exponential distribution, so we will talk about the exponential distribution, which represents the probability underlying the time interval between two incidences of an event. So it is closely related to the Poisson distribution, which was a discrete distribution, but instead of finding the number of times an event is occurring, we are now looking at the time interval between two incidences of an event, and that is why this is a continuous variable, right. The time between two events is continuous, but the number of times an event occurs is an integer, right. So this is denoted as the random variable x following the exponential distribution. Again, this is quantified by the same parameter lambda, which represents the average rate. So this is the rate parameter of the process or the event we are trying to model, and this probability density function is given as lambda times e to the minus lambda x if x is greater than or equal to 0, and obviously it is 0 if x is less than 0, because you can't have negative time between the occurrence of two different events, right. So if you plot this f of x as a function of x, right, it is 0, right, at negative values, and then it continuously decreases, right, as follows, right, because there will be less and less chance that you can go on for a very long period of time without two events happening. That is why f of x has a decreasing trend, right. So that brings us to the end of today's lecture. In today's class we looked at 4 different types of discrete random distributions, and then 4 different types of continuous random distributions, and these sort of form the basis of a lot of phenomena that occur around us, and therefore they find use in statistical machine learning. So I will end the lecture here, and I hope to see you next time.